Good morning. We have started with the highway geometric design, and today is our last lecture on the highway geometric design. So far we have covered many different aspects of the geometric design, which includes the horizontal alignment design and the basic cross-sectional details of the horizontal alignment, and the gradient, the planning process of highway alignment, and the overall policy with the highway sector. We had covered all these things in last 2 days lecture. So today's lecture we are going to cover about the vertical alignment on the vertical profile. Before I start with the vertical profile, in my last lecture someone asked about the creeper lane, how it is provided, and if we can provide any picture or any image of that. I tried, I couldn't get any better picture, so I thought of drawing it on my own. So I'm going to share that drawing. I have it here, so soon you will see that um, in this drawing. So this is little bit out of focus, and I'm going to get the technical help to get it focused. And once you see this, you'll see how the creeper lane is being constructed, or how it is being considered. Now you can see the alignment here. So the top part of the alignment is actually uh, this top part is actually your horizontal alignment, and here is the creeper lane which you are going to which you need to provide. And why you are providing this will be clear if you see the vertical profile. So vertical profile, you see that it was milder profile in the beginning, and then and the gradient increased, and if the gradient increased substantially, so that the vehicle speed is going to reduce, we need to accommodate the slow moving vehicles, particularly the heavy truck or other type of heavy vehicles. So when this needs to be included, what we do is like we add one more lane here in the as a creeper lane, where the slow moving vehicle, in our case which is on the left hand side, they will move to this third lane which is right here, and the fast moving vehicles can continue with this lane. And as the grade is again come back to normal after this point, so the creeper lane goes, and now again it is back to 2 lane. So the other direction is this side is actually the other direction, the black part, and we don't need a creeper lane because it is going downhill. So this is how it is going to look like. And we said that the creeper lane should start at the bottom of the gradient and where it is clearly visible. So you can see that where the curve starts, or and where this gradient starts, we are providing the creeper lane right at that access point, so that drivers who are driving in this direction can clearly see that there is a creeper lane, and they can also see the gradient and can get a sense that they are going to get slow. So they will be moving into the, particularly the vehicle which is going to move slowly, they will move to the creeper lane and move forward. So this was about the creeper lane. Now we'll move on to our today's lecture, which will continue. There are gradients we discussed. The gradients are going to change from one location to another, and as it changes at the transition, we cannot just leave it like that, otherwise it is going to look kinky. So we need to actually incorporate a curve to smoothen out that kink. So if in this case you see this, if you just leave it out like this, here is the kink you can see. So to smoothen it out, we actually create a curve. So this is becomes a vertical curve. So this is the first component of the vertical profile, and this curve, according to the gradient, it can be of two types. One is the summit curve, which you see here, like which is convex upward, and the other is the valley curve, which is concave or downward. Now how do we know that whether we need to fit a summit curve or valley curve? That is going to come from the gradient. If you recall last day's lecture, we said the upward or the ascending gradient is referred as positive, and the downward or the descending gradient as negative. Now the change in gradient is always the difference in the gradient from one to another. So the algebraic difference, if you see, that difference is actually positive, then you are going to get a summit curve. If that difference is negative, you are going to get a valley curve. So here are four examples or the four instances when we are going to get a valley curve, a summit curve. So in this case, the positive Ni means which is ascending gradient is steeper than the other ascending gradient which is N2 when the grade changes. So definitely the difference is going to be positive. The second case, in this the positive gradient is actually matching with a flat gradient which is 0, n2 is equal to 0. So definitely the difference is n1 and the n1 is positive, so it is a summit curve. Likewise here positive meets with a negative, so the difference is going to be positive because n1 plus n2. So this is definitely going to be a summit curve. Again, two negative gradient can also form a summit curve. So in this case, what is happening? A milder negative or descending gradient meets with a steeper descending gradient. So in this case, minus n1 minus of minus n2, which is n2 minus n1, is actually going to be positive. So it is going to form a summit curve. So we know about this summit curve. Now let's look into the what type of curve we generally provide in this summit curve. So one is that ideally we should circular curve is good because the circle we know its constant radius and therefore the side distance available is going to remain constant throughout the curve section. Apart from that, the deviation angle of vertical curves are on this is going to remain almost constant along the circular curve. But whenever we are going to construct in the field, the actual deviation is quite small, and if the actual deviation is quite small, then we can easily fit a parabolic curve which is almost like a circular curve. Why we choose a parabolic curve, simple parabola particularly? Because it is easy to do the arithmetic and find out what would be the height or the elevation at certain point. As you see the equation, I mean, you know that y equal to x square type of equation. If you know the y distance or x distance, you know what is the height it's going to be. And in the next slide or so, you will be seeing that as well. Apart from that, parabola also gives a good riding comfort. Why? Again, you need to look into, you can recall the things which we talked about in the horizontal curve. What we said in the horizontal curve is that between the curve and the tangent section, we need to provide a transition curve. So the transition curve helps to provide a transition for this infinite radius to certain radius. Now, if you look into the parabola property, it is actually doing that. So at the tip of the parabola, you have a maximum radius, and whereas as you go further, the radius actually or at the tip of the parabola you have the minimum radius or the curvature is quite high. Well, if you go far off, the radius increases, it's almost going to go to tangent and going to infinity and meet with the tangent nicely. So this is why it is going to give a good ride comfort. And for all of these reasons, basically in the summit curve, we generally use the parabola. Now, what we are going to use in the valley curve, we'll come to that later. Now, when we consider about the design aspect of this summit curve, there are a few points we need to consider. One is the user. The users are the driver and the passenger of the vehicle. So we need to look into their comfort. So how the centrifugal acceleration is helping and how it is being introduced. So as I told you that the centrifugal acceleration is going to be introduced gradually if the radius is actually decreased from infinite to certain radius. So this parabola actually does that. And it also, you need to look into the profile, how the profile is looked into. So if you are providing a parabola, it will give you a smooth profile which is gradually changing the radius, whereas circular is not going to do that. You as a driver is going to see all of a sudden there is a change. Now the other thing is that while in the summit curve, what is going to happen, the centrifugal force on the vehicle is going to act upward, whereas we know the weight and the mass, everything is, or basically it's going to act downward due to the gravity. So passengers and driver are going to feel lighter because there is a centrifugal force which is actually will make their weight lighter, quite comfortable compared to uh, when you are going downhill and there is a curve like a valley curve, when the centrifugal force is also acting downward as well as the weight. So you can think of a situation when you are inside a lift or elevator. So when the elevator is actually going upward, your all of a sudden the change in acceleration is going to impose uh, some additional acceleration is going to be downward, change in acceleration is going to be downward, and the weight is going to be pulled downward. So that way you will feel uncomfortable. So you will feel that your weight has increased and little bit uncomfortable. Whereas when the elevator is coming downward, it's the opposite reaction. So this is what is going to happen in the summit curve and the valley curve. So now let's look into the how we design the summit curve. So again, like in the horizontal curve, in the valley curve we can have two different situations. One is the length of the curve is more than the side distance, and again, as I told you, a curve is going to be designed either for the side distance or for the, or this side distance could be stopping side distance or intermediate side distance or your overtaking side distance depending on the road configuration. So one of the side distance, whichever is the governing criteria you choose, and you find out if the length of the curve is more than that, then this is how it can be estimated. As you know that the parabola equation can be well represented by y equal to ax square. So y is in this direction and x is in this direction. And how do we find the a? The a value is nothing but the exact deviation divided by 2l, which is the length of the curve. So here one thing you have to notice that in the vertical alignment, basically we measure the curve length along the horizontal distance, whereas in the horizontal alignment it was along the roadway, and this is how it has been done. So here when we say the length of the curve, it is actually this horizontal length. So now we know that we have driver eye height and the other side of the is the object height. So if we have a driver eye height h in this case and object height is small h, so this is my height and this is my line of sight and this is the other side object, then only I can see the object on the other side. So we need to find out what should be this distance, which is yours, it should meet the side distance. Now this capital H, in this case in this equation it is referred as a small h1. So h1 is nothing but a s1 square. S1 is up to this point. So it is coming from this basic equation. And h2, which is small h on this side, is nothing but a times s2 square. So s2 is from here to here. If we put back or if we now let's look into this, what is s1 and s2. So this is clearly written, s1 is root over h1 by a and s2 is equal to root over h2 by a. So the total of the s1 and s2 is going to provide me the side distance. So s1 plus s2 is, we are going to get this equation. Now this is equal to s. So if we square this parameter, then we are going to get this whole parameter, and this is going to give me 1 by a, and we already know a is equal to n by 2l. So if we know n by 2l, we can easily replace, and if we replace it, we are going to get this equation. Now our intention was to find l, which is the length of the curve. So l, we can find it out by this. Now here is the catch, we don't know the length, we are trying to find out the length, and we have assumed that the length is more than the side distance. So in this process, if we find out the obtained L is actually less than the side distance, so this process fails. So we need to look into the other process. So the other process is when the length of curve is less than the side distance. In this case, there is a portion in the which is going to be in the, then we need to formulate it. So according to the parabola property, basically if we draw a tangent here, this distance is actually half of the total distance where the parabola. So this is L by 2. Now we need to find out this one. We know the slope on this side is N1. So this is nothing but whatever the height difference H1, which is someone's eye height. So H1 by N1 will give me this horizontal distance. Likewise, on the other side, if we know the object height, which is H2 in my case, and the slope is N2, so H2 by N2 will give me this horizontal distance. My total side distance is going to be the summation of these three. So this is what has been put up here. Once we know N1 and N2, N2 is nothing but, in this particular case, this is positive and this is negative. The difference of this is going to be N1. Capital N is N1 plus N2. And if we know N1, then we can replace one value. N2 is replaced by N minus N1. This becomes my equation. Now we are trying to optimize, and the optimization we can do it by differentiating it with respect to the gradient N1. ds by dN1, if we do it, we are going to get this equation, and if we equal it to 0, then this will give me the value of the N1. So N1, we are trying to find out the optimum length. So N1 is, if we, from this equation, if we try to find out the N1, this is the equation we are, now we have to just replace this N1 in this equation, and once we replace here, the values comes like this. And when we simplify, it is quite easy. L is equal to 2s by root over 2h1 plus root over 2h2 whole square divided by n. So this equation is pretty much similar to the previous equation, some little bit of difference. So it goes on the top, and there is another factor which is 2s minus. This is what, so root 2h and this whole square, it's going to come. If you can remember one equation, the other you can easily remember. And once you know these two equation, then you can find out what is the length. So you assume one length, and if that does, after calculating it, if your assumption doesn't satisfy, you move to the other type of length, means whether the length is less. If you assume length is more, then if it is not satisfying, you go to the when length is less than the side distance, and this is how you are going to calculate. When you are doing it for the overtaking side distance, as we told you, like stopping side distance, H1 eye height is going to be 1.2 meter, object height, and you are going to estimate that. But if you are doing the same design for overtaking side distance, because you are providing overtaking, you are allowing the vehicle to overtake in your summit curve, then you need to consider the height as 1.2 meter. So driver height you have to replace object height is equal to 1.2 meter. So both heights are going to be 1.2 meter. And now how to set out the curve, summit curve? Basically you are going to look, you know the tangent part, and from there you can look into what is the angle it is going to come up. So in the survey, you just find out what should be the elevation at various intervals, and as you go, you just make sure these elevations are meeting, and you just try to smoothen it out. That is how it is laid out in the field. Our IIC actually made our life simple. How to find out this length of curve. So how did they do it? So here in the x-axis there is a deviation angle, and then there are various vehicle speed, which is in this direction, and this is the m. M is nothing but, you have to, again I'll go back to this curve. So m is nothing but the distance from the this change in gradient to the top of the curve. So this distance, if we know, then we can actually find out what is the length of the curve. Or if you want to lay out the curve, you can actually find out this way. You know the length of the curve from the drawing and the design, you know other factors, and you can find out what is m. So you know that elevation, and gradually you just fit in based on your y equal to ax square equation. This is for the stopping side distance. Similar curve is also available for the intermediate side distance and overtaking side distance. So this will make the calculations easy. Now that completes our summit. Now we'll be moving to the valley curve. As I had explained you, the summit curve and the valley curve, the difference is the algebraic difference, and if the algebraic difference is coming to be negative, then it is going to be valley curve. So we have four instances when we can get a valley curve. So a descending gradient, steeper descending gradient meets a milder descending gradient. So N2 is positive, but N1 is negative. I mean, both are negative, but if we subtract it, N2 becomes positive and N1 will remain negative. So N1 is always greater than N2 in this particular case. Definitely this will result in a negative value, which means we are going to get a valley curve. Likewise, here descending gradient meets a flat gradient. So flat means here is 0, N2 is 0 and N1 will remain negative. So this is again negative. Now a descending gradient meets a ascending gradient. So the ascending gradient is positive, which is N2, so N1 minus N2, this will remain negative, and this N1 is already negative, so overall N value is going to be negative. So it is a value. The fourth one is this: we have a milder ascending meeting a steeper ascending. So again N2 minus N1, this is the ultimate expression where N2 value is quite high, negative value, and N1 value is lower, negative value. So together it's going to give me a negative value, which means that we are going to get a value. Now again we are going to in the valley curve we are going to consider the side distance. Now if you are considering the side distance during daytime, actually the whole curve or whole roadway section is visible. However, what is going to happen in the night? The roadway section is visible only on the headlight. So it depends on the headlight, how far the headlight can go and how far the headlight can reach, and that is the amount of highway or the section is visible to the driver. So this is why the headlight side distance is critical for valley curve, which was not for the other cases as such. So then we need to estimate the valley curve length based on the headlight side distance. And how should we do that? Before we get into that, we need to look into the comfort criteria. So there is another thing that, as I told you, when a vehicle is going downhill and when it is meeting the curve down there, the centrifugal force is acting downward, as well as the weight of the person and the vehicle is also acting downward. The summation of this total weight is actually increasing the weight of the person or the vehicle, and they will feel discomfort. So we need to consider this comfort criteria. How do we estimate the comfort criteria? We need to look into the change in centrifugal acceleration. So the change in centrifugal acceleration is this. The C is the centrifugal acceleration, and the change is going to happen. So the change at the curve at the bottom, it is going to be v square by r, where r is the radius. At the tangent, when the curve began, at that time it is 0 because r is infinite. So this is the total change, and this is happening over the time t. So this t is nothing but the distance divided by the speed of the vehicle. So if we replace this t here, then centrifugal acceleration is going to be v cube by l r. Now from this we can get L, the length of the curve, as v cube by cr. Another part, we know that we are saying r as the radius. R in this case is nothing but L by n. So L by n, you just need to understand this, we are considering the half part of the curve, not the complete part. This L by n, if we replace it in this equation, then it becomes L is equal to n v cube by c. So this is the half part. There is another half, so we need to multiply with 2. So the total, it becomes 2 times n v cube by c. So this is based on the comfort criteria. At least this length should be provided in the valley curve. Let's look into the side distance criteria, how it works. As I told you, the side distance criteria, we have to look into the headlight. So the headlight is going to go straight. So in this particular figure, if you see the red line, this is straight, and there is little bit of deviation. If you look into the projector inside the headlight, so they are at certain angle, and because of that angle, the light is deflected little bit on the upward side as well with an angle alpha. So if we know this alpha angle, and which is we generally know from the manufacturer specification, and is generally close to 1 degree or 2 degree, mainly it is 1 degree, and then we can easily find out what is the length. So the length in this case, it is going to be, if you we are trying to find out if the vehicle is here, how far it can see. So the vehicle here, it can see is the height of the eye, which is here up to this much, and the deviation of the headlight, which is S tan alpha. So this is alpha, then this is S tan alpha, and this is the distance headlight. So if this is my distance, then S tan alpha plus h1 is the total height which you can see. This is again, if you look into the parabolic equation, it is nothing but a times s square, which is my side distance. And a, as we know from the parabola equation, basically it is going to be n by 2l. So if we replace this s h1 plus s tan alpha is equal to n s square by 2l. So from this, if we just try to find out what is the length is going to be L equal to n square by 2h1 plus 2s plus tan alpha. Now one thing you have to understand here is that this 2l, whenever n by 2l we are considering it, we are considering the complete length. So 2l is the total length. So so this length is going to be L times this one. So this will give you the length of valley curve when the curve length is actually more than the stopping side distance, or just the side distance. S is the side distance. If you need overtaking side distance, you have to provide the overtaking side distance. If you need intermediate side distance, you need to provide the intermediate side distance. The things changes when the length of the valley curve is actually less than the side distance. So in this case, you have to accommodate the tangent part as well. So here this distance or this distance will remain same, whatever the height of the eye, that will remain same, and what is the angle S tan alpha, that will remain same. So the left hand side remains same, whereas the right hand side, which is you are trying to find out the horizontal distance x component, there it is going to change. So there are two components, S minus L by 2. So S is the total side distance, and L by 2 is the portion of the tangent, which is going to be here, or if you recall the summit curve, it's L by 2. So this is the portion which is going to remain in the tangent, and times n, that will give me the distance in the horizontal direction. So these together, if we try to solve this one, we'll get the length as L equal to 2s minus 2h1 plus 2s tan alpha by n. So this is again very much similar to this one. Just if you try to see the difference, you will easily recall that how this difference is coming up and what would be the this distance. So here is n s square, here in the denominator it is only n, and this parameter remains same, which was in denominator it went to numerator here, whereas the whole term is negative and it is subtracted from 2 times the stopping side distance. So this is how we calculate. Now before I move on to the next slide, I got a question. Does the position of sun affect the calculation of stopping side distance or OSD? The position of the sun does not affect, because whatever the position, you can still see the whole region. If your position of the sun is actually obstructed because of the hill and it is going to get dark and someone needs to turn on the headlight to see the road, yes, at that time it may affect, and that needs to be considered. So it's more, again it is coming back to the headlight, not the sun. As we had shown you some graphs how to estimate the these distances for summit curve, we have similar thing for the valley curve as well, and the curve is quite simple, or the similar way. you have the speed on this direction, you have the deviation angle, this is the length, and from there you can easily find out um, what is the length of the curve and what could be the speed in that particular region. So this uh, so in this thing, another which I'm not covering or which is actually understood is that the side distance. So the side distance estimation, you have to recall on the first day's lecture when we said that how we are going to estimate the side distance uh, for stopping, for overtaking, for intermediate. So we have to use those equations to find out the side distance and use whatever the value we are getting there, we have to use it here to find out the length of the valley curve. So that is the complete process, and if you find that it is not meeting the length, then again you have to go back to the side distance. Suppose if it is not meeting if it is not meeting due to this comfort criteria which we had discussed earlier, like for this region, then you have to revise the length, and based on the revised length you have to find out what is the revised side distance, and based on the revised side distance you have to go back and see if you really need to impose some speed limit on that particular curve. So now if I move to this summary, before I move there, there is another question. If stopping side distance is not given, how can we recognize whether length of valley curve or stop is more or less than the stopping side distance? So as I told you, the speed of the vehicle will be given, and if you know the speed of the vehicle, you can actually calculate the stopping side distance or whatever the side distance you need according to the process which we had discussed in our first day's lecture. So that needs to be calculated and then used it here. Now coming to the summary of the valley curve, basically cubic parabola is the most common thing which is preferred in the valley curve, but our IRC says the square parabola, which is like y equal to ax square, and that is why you see most of the equations are based on that. So if you are using the cubic parabola, this is how the equation is going to change: y equal to bx square, where v is equal to 2n by 3l square. So you can just replace these values at whatever the derivation we did for the square parabola, and you can see how things are changing. Now another point about the valley curve which is quite important is the lowest point. So valley curve leads to a lowest point at certain location, in particularly some of the valley curve, and this lowest point is critical because you don't want the water to get stagnant there, and the water is coming on the road. So this lowest point you have to ensure that there is enough drainage, cross drainage and longitudinal drainage, all these, particularly the cross drainage, so that the water can easily flows out of the roadway. So this is one thing. And how to find out the lowest point? This is actually done if it is unequal grade, it is, you can find it by this, the distance L times n1 by 2n into power or to the power 0.5. It will give you the distance where the lowest point is going to happen from the tangent point. If you find out, you have to just go there as a field engineer and see whether there is any cross drainage structure and how it is, whether it is adequate or not, so forth. Now before I move on to the next slide, I received another question: what would be the minimum distance of a bus stop if need to provide at a valley curve or summit? This is a very good question. The bus stop means, you mean to say the where it should be provided and how. So the bus stops are provided according, first of all, according to the convenience of the passenger, where they have crossroad and where they are going to act. Now if you are providing a bus stop, first of all you need to make sure that it is at a considerably flat terrain. At all you cannot meet the flat terrain. Whenever you are providing the bus stop, you have to see whether you have enough distance so that the bus can actually come to dead stop at the stop location. So this enough distance is going to be in the what we said, that there is a like extra lane which you are going to provide. It's a lane on the side you will be providing to the bus stop, and this lane, if you have enough distance, so the bus can actually come out of the main line and go to this deceleration lane, and in the deceleration lane basically it will slow down and come to the stop. So this is what you have to take care, and and this can be calculated based on again the stopping side distance, and so basically your deceleration lane should be at least up, and then you can take care of it. I hope I answered that one. Now the another question was that why operating side distance is not considered for calculating length of valley curve. Sorry, why overtaking side distance? So the overtaking side distance, I'm saying that overtaking, we are not going. What I tried to say here was that these equations are for side distances. So if you need to provide overtaking facility along the valley curve, definitely you need to consider overtaking side distance instead of S, which is here it is stopping side distance. You can need to provide overtaking side distance. So there is it all depends on like whether you want to provide intermediate side distance, overtaking side distance, or stopping side distance. So this is just an instance. If you are considering stopping side distance, that is how it is going to look like. So depending on that length, you are going to provide this equation. Other than that, it is going to remain same. Now I got another question. Can you tell about us how highway or designing in field of highway engineering and in terms of design? So I'm trying to understand this question. Highway of designing in field. So is this how the highway design in the field is different from the highway design what we learned so far? I'm guessing that is the question. So the answer is that in the field, when they are in the not in the field, or actually these highways are designed in the design office using various software, designing software, and some of the popular softwares are Civil 3D, MX Road, InRoads, then there are Geopack, there are X number of other softwares which can be used. And these softwares actually does all the calculations or whatever we did or whatever we learned here in the background and provide the highway. As a design engineer, we need to select the proper point of intersection where the curve is going to be there, and we need to provide the proper vertical point of intersection where the vertical curve is going to be there. And the softwares are nowadays smart enough to tell you where it is actually not meeting the design criteria, and it will show you in the red, and as a design engineer you just need to go and see why it is not meeting, and accordingly you need to change by trial and error method, changing the PI location or fitting with a different curve, or if you need a design exemption from the speed point of view, all those things you need to do. So that is how it is being done. But when someone is reviewing the design, they are recalculating it, some of the thing as a proof check, they again go back to this basic understanding, and from this basic understanding they calculate the radius, they look into the side distance, they look into other details for that. The extra widening is also again can be done by the software, but you have to tell the software that you provide the extra widening using certain formula, certain guidelines. You also have to tell the software that how many lengths you are going to provide and so forth. Now few other questions which I got, one is that for safety point of view, which curve is more feasible, valley or summit curve? So comfort point of view, as I told you, summit curve is better. Now from the safety point of view, it all depends on the speed. So if you are at a higher speed than the speed which the curve is designed, if you are on a summit curve, your vehicle can be thrown off from the road. And on the contrary, if you are at a higher speed than the speed what a valley curve is designed, so when it is negotiating the valley curve, the bottom point, your car's suspension system can bottom down and can hit the bottom of the road. So either case there is a safety issue, and it depends on how much it is, how far, I mean how higher speed you are going to go. Yes, now another thing is that if you are going to the valley curve, naturally because of the downhill gradient or descending gradient, your speed is going to keep on increasing. So if you don't check, then definitely that is where the safety the vehicle can get into accident. So this becomes more critical than the summit curve, because in the summit curve, once the vehicle is going as in the ascending gradient, naturally because of the ascending gradient, the speed is quite checked, and unless someone is actually pushing the accelerator too much, they are not going to overspeed like easily. Here in the valley curve, without even pressing the accelerator, the vehicle can. So the next question was, what will be the effect on road if the design consideration of summit curve is not suitable? So if the design consideration of summit curve is not suitable, then it means the speed is not considered properly. So as I told you, if someone is traveling at a higher speed, the vehicle can be thrown off from the summit curve. So that is the major thing which is going to happen. And the other thing is that if it is not designed properly, if particularly if it is not meeting the stopping side distance, so if there is any object lying on the other side, a stationary object, the vehicle may not be able to see and get into accident. If you have provided overtaking zone, and if it is not designed for that height, so again it can get into accident because it cannot see the oncoming vehicle. The other another question which I received is, the valley or summit curve increases the effort, then how is it beneficial? Can we alter the gradient? The valley curve is for the vehicle point of view, valley curve is not increasing the effort at the time of going downhill. It's only going after negotiating the valley curve, when it is coming out of the valley curve, and if it is ascending gradient, that's summit curve. When it is going towards the summit curve, actually the effort is increased. So once the vehicle negotiates the summit curve, then it is actually eased out. Now in both cases, basically we are doing this thing because there is a change in gradient. Now you can flatten out the gradient. What is going to happen? Your earthwork is going to increase and your construction cost is going to increase. So I'll come to those things. I mean, I have already told, and I'll come to those things like flatter gradient, what is the effect, and when we actually see the next few slides. Where another question is, which curve will be provided? So it depends on your gradient, which curve is needed there. So in the mountainous terrain, both type of curves are going to be there. Valley or another question which I received, if we will provide small trees on the median of a valley curve to prevent the glare of headlight, then no need to calculate the length of valley curve for headlight side. The headlight side distance is not for the glare from the opposite. It is the headlight. When the headlight of the vehicle which is traveling falls on the road, then only they can see the road, and then the vehicle can travel. So it is their own headlight. It's not for the other headlight. So the small trees or the bushes which you provide, the shrubs along the median, that is only helping the glare which is coming from the other side. So that is a different aspect altogether. That is not part of the this design. Now we need to look into how we can combine the two alignments, or the horizontal alignment with the vertical profile, and this is quite critical because if you want to understand the highway design, basically you have to provide both things at various locations, and when you are providing, you should actually follow certain norms. Then only the design is going to be safe and then good. And this is why the general statement is horizontal and vertical alignment should complement, and when we complement, we should actually have a proper balance between the curvature and the grade. And when the proper balance happens, we can actually avoid these two situations, like excessive curvature to achieve flat grades, which someone was asking, like if both are vertical and summit curve is so difficult, then why can't we flatten it? This is it should be avoided, because then that will introduce excessive curvature in the horizon, and excessive grades to achieve flat curvature. So this is also not advisable, like excessive grade to achieve flat curvature. So which means that you are connecting two cities and there is a hill in between. So to make your road straighter, you want to go on the top of the hill straight and again go down on the hill straight. So this is also not advisable. Or if you want to again negotiate this hilly terrain, basically you go towards, if your these two cities are on the north and south, basically you go too left, too east or too much west to avoid the hill. So that is also not avoidable, advisable, because it's going to increase your. Now the other point is like sharp horizontal curve should not be introduced at or near the top of bottom of the pronounced summit or sag curve. So if you introduce this thing, many times the curve, horizontal curve, gets hidden behind the summit or the valley curve, and particularly the summit curve. And when it gets hidden, diver may not perceive that there is a curve. They will be expecting, okay, they went uphill, now they are going to go downhill, and this horizontal curve will come as a surprise to them. And also we have to understand that at the sag vertical curve, or at the summit valley curve, basically the vehicles are getting, the speed of the vehicle is quite high, and all of a sudden when they're high at a speed and then they see a horizontal curve, so they need to that speed may be quite higher than the for that horizontal curve. So that will be again pose a problem or safety concern for that curve. This will actually result in a erratic motion and can get into accident. So this is the situation. And also, as I told you, the intersection or the bus bay or the truck lay-by, all these things should be provided almost, should be avoided on the curb and also in the higher gradient. So it should be provided in a flatter section and as much as possible, and all or in a flatter curve. So now we'll be looking into some of the combinations and how we should be balancing out. So the balance should be done, horizontal curvature and grade should be in proper balance, as I told you. Maximum curvature with flat grade or flat curvature grade should be avoided. So that is there. Now how will we coordinate? The vertical curvature superimposed upon horizontal curvature generally results in a more pleasing appearance and reduces the number of side distance restriction. So you will see some of the images, or where you will see if we do that how it is helpful. Now successive change in profile, not in combination with horizontal curvature, may result in series of humps visible to the driver. For how this is going to happen, some of the perspective, here are some of the images. So you have like curves like this, and it is in a flat gradient. So how the perspective view is going to look like this. The next curve is not going to be visible for the driver from this when they are actually negotiating. When they don't see the road, of course they are hesitant, they don't know whether what is the curvature amount, and there will be an operation effect, means they will be slowing down, or if they are coming at a high speed, they will be drastically trying to slow down, and the vehicle can go off. So these are the another thing is like if there is a horizontal alignment and you don't provide a curve and the vertical end is flat, so then this will look like this thing. It's not a pleasing appearance, and the driver will behave. So if you provide a curve like this, then it will look smooth and it is going to be smooth ride. So before I move on to the next, I have another question. In which type of condition we can provide valley curve? So it depends on the depends on your gradient. So as I told you, if your gradient, the difference of the gradient, algebraic difference of the gradient is positive, you are going to provide a summit curve. If your difference is negative, you are going to provide the valley curve. So I'm not sure why the sound is echoing, because we don't have any microphone here or a speaker here, so it could be somewhere else. So hopefully now you can hear better. So let's move on to the next slide. Another condition of coordination is with the environment or the area through which a highway is going. It should be you should actually see what is the scenic thing is there in the highway, and when possible, so we should actually, when possible, alignment should be enhanced scenic views of the natural man-made environment. How we can do that? Highway should lead into, not away from the outstanding view. So if you have a river like this, if you are actually constructing a highway straight line like this, which it is nice, but it is not actually meandering along the river, but if you do this one, then it is going to be quite pleasing. So that is why we are saying that highway should lead into, not away from the out. And how we should consider, it should fall towards features of interest at low elevation and rise towards feature best seen from the below or in silhouette against the sky. So things which you like to see against the sky, like the mountains and all those things, at that point if you have a gradient, upward gradient, that is quite good. And if you want to see a river which is down there in the valley, so if you put a descending gradient, that is quite good. Then the other condition which is going to come up is here. So if you have a alignment like this or the horizontal alignment like this, there is a curve and then there is a tangent section like this. So when the vehicle is here, it can actually see the this portion of the highway, the tangent, and particularly if it is a of this gradient in this portion. So they are actually sitting here, they are seeing the upward, so they are seeing it from the side, and when they are seeing it from the side, if there is a vertical curve like this, so what they are seeing is actually the bumps, and when they see the bump like this doesn't come very well to the driver. They will see it as a bumpy road. But as a design engineer, we want to create a smooth road. So what we should do here, actually we should provide try to smoothen it out by this dotted line or balancing it out, not to provide too many vertical curves like. So this is how we can coordinate. The next thing is the coordination of the PIs. So here is my horizontal alignment and here is my vertical alignment. So the PI of this horizontal alignment is here and the vertical alignment is here if it is matching, and if it is on this direction, and this is a summit curve, and this is in this direction, this is valley curve. So altogether this is going to give you a pleasing right condition. Whereas if it gets slide little bit, and if it is not properly coordinated, if your PI, vertical PI, is shifted little bit here and this one, then it is going to be difficult for the driver as well to negotiate. As we remember that we should actually provide the curvature, horizontal curvature, right on the top, not on the other side of the vertical curve, or right before the summit curve, not on the other side. So this is what is actually we are coordinating. If we move it other side, it is going to be difficult. So you have to consider the roadway which is going from one direction to the other. So you have to consider both side traffic. So I got another question, I mean the same question, which is in which type of condition we can provide value or summit curve. I think I have answered, saying that it depends on the condition and depends on all this perspective issue. You should consider which curve. There is no hard and fast. I'll say that you have to provide vertical curve or you have to provide summit curve, but depends on the gradient and so forth from which you can see that what curve you need to provide. So here is another condition, like if you have a horizontal profile like this tangent and a curve, and in this curve you also have a valley curve. So when someone is traveling in this tangent section, their eyesight is going to be like this, so this portion is going to be totally lost, and when they get lost, this is what they don't have any idea how the road looks like here. So it's complete box type of thing. This should be avoided. So the way the good practice of designing is that in a horizontal, in a clear view, there should not be more than 2 breaks, means 2 curves, and in the vertical there should not be more than 3 breaks or 3 curves, like here is 1 break, here is another break, here is another. If you try to follow this type of thing, the road is going to be pleasant and it's going to be nice. And again, I'm going to come back to the design aspect which we had discussed in our very first class, or shown in the very first class, how the horizontal alignment and the vertical profile is going to look like. Here is the plan where you have the alignment, the tangent part. It's going to show all the lengths and the median and the details of that. This is actually designed using some of the software, and the software in the background, it is doing all the calculations which we have learned so far. And if you don't know the calculation, if you just rely on the software, then the problem is that depending on the condition, you won't be able to change the criteria, and you won't be able to know why the software is saying that, giving you the warning and how to take care of the warning. Because if it doesn't meet certain stopping side distance or the side distances, or if there is some issue, it's going to give you the warning. And the warning, if you want to take care of it, you need to know the design. So this is the vertical profile of the horizontal alignment, the same one. So here here is one gradient, here is another gradient. So we are providing a vertical curve here, which is shown in this vertical profile, and this curve, once we provide that, basically it is a valley curve, and we look into the other factors. What is the, here it is, we are looking into the horizontal. There we can actually, whenever we are reviewing it, we can see whether there is a horizontal curve as well or not, whether it is properly coordinated or not. So here, as I told you, in the valley curve, we have to be careful whether there is any cross drainage structure, because this is the critical point. Water is going to come down from this side, and this side we need to make sure they has adequate drainage. And here you can see the cross drainage structure. So when someone is reviewing or someone is designing, needs to make sure that there is a cross drainage structure and there is sufficient provision for water to flow out. And this is the complete criteria of that. As I told you, the intersection should not be on the curve or on a flat section. So this is some condition where we are not putting the intersection right here, but before the curve. Another thing we are seeing that the intersection, wherever it is meeting, it is actually on a bit flatter terrain or flatter gradient. So this is how we ensure and make sure the design is proper. So with that, my lecture ends for today, and there will be a proctored quiz after this, and if there is any question, I'll take few questions. So the first question which I received right now is what are the various softwares for highway geometric design? Various softwares are, there are few Bentley softwares and Autodesk software. Autodesk software is called Civil 3D. Bentley softwares are MX Road, InRoads. So in India we use MX Road. Europe also to some extent they use MX Road. In US they use InRoads. There is also another software from the Bentley and Geopack. Nowadays they are moving into the open roads type of software, which can go in any direction. Now, where this question is coming, I don't know what is negative super elevation. Negative super elevation is part of railways, not part of highways. But in highways, in some condition, we may need to provide the super elevation which is in a different direction. So it is much prominent, and it is actually much more there in the railways, because the branch out can happen on the curve, whereas in highways we have better control and we don't want the branch out to happen on the curve but on the tangent sections to avoid any negative super elevation. So the super elevation, if you need your outer edge to be raised, in case if you because of certain constraint you are not raising your outer edge but you are raising your inner edge, that is your negative super elevation. One more question I got: can we decrease speed instead of doing such horizontal or vertical alignment design? Yes, you can decrease speed, but how? At certain critical condition, you may need to decrease speed, but decreasing speed is actually not meeting the driver's expectation. Because if you are giving a highway and ask the driver, hey, I have constructed a highway, this is expressway, and you can travel at 100 kmph, and then you put a section which will require the driver to come down to 40 kmph. Is it going to meet the expectation? Because the driver, when they are on the expressway, they know that okay, I can drive at 100 kmph. So that is not the good solution, but yes, in some extreme cases you may need to do that, but it has to be done with caution and it has to be looked into. And if you look into the statistics, accident statistics or the safety statistics, most of the places where the accident happens, where the speed is reduced drastically. Another interesting question I got: if any religious place becoming obstruction in design, then alternate ways are there for alignment. This is related to the policy of a country and the process. So most of the countries in the world, they say if there is a established religion place or historic place or environmentally preserved locations, all these things needs to be avoided, and you need to have less impact when you are deciding the alignment. So this comes under that category. So and this will look into the cost benefit analysis as well. So after you consider all these things, then you can be you can look into that. So okay, so someone said that reducing speed can be economical than increasing elevation for highway. So reducing speed is economical from the construction point of view, and as I told you, alignment needs to be designed from the operation point of view, from the overall cost of point of view, user cost point of view. So reducing speed, if it leads to hundreds of accidents every year, and if you add that cost, do you think it is going to be still cheaper? You need to do the life cycle cost of that. So construction, yes, it is cheaper, but other cost is going to bump up the cost, and as far as our experience, it is actually expensive if you consider the life cycle cost. So that one more question, whether transition curve can be provided between summit and sag curve. So transition curve, if you are providing a circular summit and sag curve, yes, you may need to provide the transition curve. But if you look into the radius of this, if you are providing a circular curve, the radius of this circular curve in summit and sag curve, these radiuses are quite large, and it can be easily bond with the tangent section. So eventually you don't need some transition curve because of the large radius. The same thing which we said for the horizontal curve, if the radius increases beyond certain point, you don't need transition curve. And most of the cases in the vertical alignment, the radiuses are so large that it is actually not needed. The other part is like if you are providing the parabolic nature, the way it is, it takes care of the transition. So that is the whole point of considering the vertical curve as the parabolic, the square parabola or cubic parabola. Another question we got, can we attend some certificate courses related to highway design at your center? So this is a center related question. QEEE members, we do if no side distance is available while designing in hilly areas. So if not, you have to provide some side distance, the minimum side distance. There is no road without no side distance. So if you are designing that, that's not a design actually. It's just you are wherever you can lay a road, that is what it is. So the whole design purpose is you have to make sure that the side distance is there. Now if you cannot meet the side distance for certain speed, as I told you, in some extreme condition, you may need to reduce the speed, you may need to look into some other alternative options. And this is, again, there is no straightforward answer what alternative option, how we are going to consider. It varies from site to site. The other one more question, do we provide super elevation on valley and summit curve? So how do we provide the super elevation? Super elevation is to provide increase the outer edge, and so that you can take care of the centrifugal force. So in summit and valley curve, if it is just pure summit and valley curve, your centrifugal is acting either upward or downward. So how we can raise the edge to do this? You can think about it. Of course, if there is a horizontal curve on this summit and valley curve, for that horizontal curve, the centrifugal force is acting outward, and for that you need to raise the outer edge, and there you can provide the super elevation. Another question, why do we provide flexible pavement for airport runway and not rigid pavement? So I'm not this question is related to the airport, and I'm teaching highway, so I defer this question whenever you are taught the highway. So the question number 4 is about the stopping side distance. So the question number 4 is about the stopping side distance, and if you recall, we had discussed about stopping side distance, how to estimate that, and in that estimation process, we need to know the acceleration due to gravity, which is g value, vehicle speed, friction factor. We also need to know the lag time. So here this reaction time or the lag time is given 2.5 seconds. Acceleration due to gravity is given, which is 9.8 meter per second square. In this particular case, it's a down gradient, means expectedly your stopping side distance is going to be more, and there was a formula f plus minus n percentage. So that n percentage is given, and in this case it is descending gradient, which means your denominator should be less, which means n or descending gradient is negative, so you have to use minus n. And you have to be careful about the vehicle speed. So the formula which we discussed mostly was for meter per second. However, here it is given in kilometer per second. You have to appropriately convert it into meter per second. Question number 5, which is about designing super elevation for a horizontal curve. So we have the radius is given, design speed is given, then we have asked you to follow the IRC method. So if you recall the IRC method, you have to consider the 75% speed without ignoring the friction factor, right? So once you ignore the lateral friction factor and try to find out what is the expected super elevation, and if your expected super elevation is within 7%, you are good. If it is more than that, means you have to restrict your super elevation to 7% now, and for the full design speed or 100% design speed, you have to find out what is the expected lateral friction coefficient. So in this, if you find out the lateral friction coefficient is actually more than 0.15, you need to go to step 3. If it is less than that, you are good to go, and that is what the super elevation you are going to provide. Now in case if it is more than 0.15, what you need to do is that maximum lateral friction you can consider is 0.15, maximum super elevation you can consider is 0.07 or 7%, and when with that you have to recalculate what is the design speed this road should have. So based on that, you will get a different design speed which could be less than the original design speed which you used for the design. And whatever the design speed you get there, you have to consider the speed, because in the roadway you will see the speed in the multiplication of 5. So you are not going to go on the higher 5 but the lower 5. So if it is coming 98, the design speed or the posted speed should be at least 95. If it is coming up 92, we'll be considering it as 90. Likewise. Question number 6, which is about 2-lane highways, a horizontal curve radius of 250 meter and the total pavement width of 7.5 meter at the curve. The minimum side distance of 240 meter is to be provided at the curve. Assume the length of the curve to be greater than the side distance. Determine the setback. So the question number 6 is about to find out the setback distance. So if you need to find out the setback distance, as I told you, the radius is actually the central line of the roadway. Now your if it is a 2-lane, 7.5 meter means 2-lane, is at the center, means there is 1 lane on the left side, 1 lane on the right side. Now a vehicle is going to see, whenever it is traveling, it is actually middle of one of inside lane. So you have to find out the distance which is at the middle of the inner side lane, which is small d. The small d distance is going to be 7.5 meter, means which lane is going to be 3.75 meter, and 3.75 meters half is going to be your d distance. And if you recall the formula which we had, from there if you put it properly, first you need to calculate the angle, which is alpha, and if you calculate the angle properly, and then if you fit into the offset distance m value, then you can get the setback distance. So now we'll move to the question number 7. So question number 7 is about grade compensation. So we talked about we need to do the grade compensation. So in this case, there is a ruling gradient of 6%, and also there is a horizontal radius, which is 60 meter. Now if you recall, there is a minimum grade compensation and there is a maximum grade compensation, and also there is a gradient beyond which you don't need to do the grade compensation, which was 4%. And a minimum, there are two formulas in there. If you look into those two formula, you will get the minimum and the maximum, and if you from there you need to choose whichever is there. For the 6% or for the 60 meter, you'll get some grade compensation, and whatever that value, you need to deduct it from 6 and find out what will be the compensated grade. So that compensated grade you are going to provide. Now in case that grade compensated grade is less than 4%, you don't need to go beyond 4%. So the grade which you are going to provide is going to remain as 4%. So that is how it is going to. And so that you have to do the same exercise again when it if your ruling gradient becomes 5%. So that was about question number 7. Now we'll move to the question number 8. Estimate the psychological widening required for 2-lane highway with lane width 3.5 meter at a horizontal curve of radius 200 meter. Assume design. If you recall the extra widening required, there were two parts of the extra widening. One was the mechanical widening, another was the psychological widening. The psychological widening had a empirical formula through which you can find out. And the other mechanical widening, it was derived based considering the length of the axle and so forth. So here the question is about the psychological widening. So in the psychological widening, they need to find out, you need to just find out using those empirical formula what should be there, and that needs to be added to the pavement width to give you the psychological widening. Another thing about the psychological widening, if you recall, if it is more than one lane, then only you need the psychological widening. So here it is 2 lane, definitely you need psychological widening. So that is what is about question number 8. Now if we move to the question number 9, the question number 9 is about designing the curve length based on the comfort criteria. So this is about a valley curve where you have gradient change in the gradient, which is capital N is given 5%. You have to find out the length of the valley curve for certain design speed, which is 60 kmph, and centrifugal acceleration rate is given, which is C value is 0.6 meter per second cube. So today we derived how to get the length of a valley curve for certain centrifugal acceleration rate and the speed. So in the end of the derivation, we found out the length of the valley curve will be L equal to 2 times certain factor was there. So that is what the equation you have to use. By understanding that, you can actually solve question number 9. Now the last question, question number 10, is about finding the length of summit curve for stopping side distance of 180 meter and at a junction of a rising gradient, so and the falling gradient. So you have an ascending gradient of 1 in 50 and a descending gradient of 1 in 30. So from this you can find out what is the capital N value or the change in gradient, what is happening. Once you know that, then you need to find out the summit curve. So summit curve depends, there are two different formula in which you need to find. One was when summit curve is more than the side distance, another was when the summit curve is less than the side distance. You start with one assumption, either more or less, and see whether your assumption holds good or not. If not, you have to move to the other one, and definitely the other one is going to be good. So based on that, you need to find out. Now in this case, we have said it is a stopping side distance. So stopping side distance means your H1 and H2 in that formula. If you see, the height of one is going to I is going to be 1.2 meter, and whereas the height of the object is going to be 0.15 meter. So based on that, once you calculate, you will get the summit curve length. So this is all about the 10 assignments. Any question? So I already got a question. The question is, does overtaking side distance any affect by any gradient? The overtaking side distance, if you consider the gradient, yes, it does affect. Now the thing is that the effect is mutual in the way like the oncoming vehicle, whenever it is coming, if it is coming in downgrade or descending gradient, the overtaking vehicle is actually going in the ascending gradient. In that case, basically whatever the time it is taking for the ascending and the descending gradient, that there it needs to be considered. How much time it takes to that capital T, which is actually the time which it takes to overtake. So in that overtaking process, if the acceleration rate remains same, then the effect is not going to be. But the acceleration, if the acceleration rate changes based on the gradient, if we have that information, then definitely the capital T is going to change, and accordingly we have to revise the. But in general, like when you are solving the problem, mostly you won't get a different acceleration rate for the gradient. But another thing you have to consider is like the same road, the same overtaking operation can happen in the other direction. So if the overtaking is happening in the ascending gradient, the overtaking can also happen in the descending gradient. So keeping both things in mind, someone needs to consider what is the critical one, and accordingly you have to consider the overtaking side distance. Now once you know the overtaking, that's all. Thank you very much to all of you.